I'm going to post this video because what I was doing is a little bit of a follow-on to my earlier video on integrators, in which I was doing something the author suggested you do, which is check out how much error the integrator would accumulate over a period of time by shorting the input. So that's what I've done. This red wire is pin 3 of the integrator, and I'll show you the original circuit so you get some idea what we're talking about. It's pin 3 there, and there's the integrator, and I've got the I'm checking the output. So however, I'm doing this introduction after having done some of the experiment and coming up with a surprising result. So take a look at this, see if you see something that you might be able to help me with or our viewers. I'm now testing the stability of the op-amp that's being used in this integrator circuit. What I have done is grounded the input to the integrator, and as you can see, the meter which is connected to the output shows that the output is 0, which it should be because the power supplies are turned off and it's been sitting for some time. So pretty much everything in the circuit has discharged. Now I'm going to go over here and maybe hard to read. I'm going to turn the master enable on right there. And pardon the swift camera work. You see that the output has gone to 5.5 millivolts, and now it's going to begin to drift. So what I'm going to do is let that drift for a while and allow everything to stabilize. Now it won't stabilize. What I mean by stabilize is allow a lot of time to go by, and then I'll come back in every few minutes and check the level and give you kind of an update, and we'll see how this integrator performs with a shorted input. I thought while we're waiting, and the meter powered off a little bit ago, so I turned it off. We'll turn it back on in a little bit. What the author believes is going to happen. Now understand, this is worst case, but his calculations are that the VOS, that is the offset voltage that the amplifier has, will produce an error that will be integrated, and that both the input follower, go back and look at the circuit for a minute, both this input follower and the integrator itself will have that offset error. And so his prediction is that worst case, this output will integrate an error at a rate of 1.6 volts per second. However, that's not at all what I'm getting. I'll turn the supply back on, or the meter back on, and you see we're still getting the same 5.6, 5.7 millivolts. Now, if I put my finger on the IC, it'll, heats up, it'll change, and things like that. But I'm trying to not perturb the circuit at all and see how bad whether it integrates very much error. And I have to say that it's been a while since I powered this up. It's still turned on, it's still producing an output, but it's not seeming to accumulate any error. And what that tells me is that perhaps we've gotten lucky. In other words, it may be that the particular IC that we have in this circuit, that MC3403 that we have right there, has very, very low offset voltage. Let's take a look at the spec sheet for that op-amp and see what it says. Here is the spec sheet for the MC3403. You see there the input offset voltage and the input offset current. It says a typical is 2 millivolts. I'll go over to the right in a minute. And notice what I'm talking about is this figure right here, 2, and this is 30. And we go over to the right to see what that is. That's nanoamps and millivolts, respectively, for the 3403. Now, there is no minimum specified. So let's take a look at the meter again, 4.6. Now, what I'm going to do is just wave my hand over the integrated circuit a little bit and see no, it doesn't seem to change much. Well, it did go down to 4.5. So it has gone down a little bit. But this particular integrator actually is quite stable. It should integrate any error. And by I say integrate any error, if there's any variation from 0 that is a constant variation, in other words, a variation in one direction, even if it's down in the microvolt range, that should slowly over time accumulate in the integration capacitor, because whatever that voltage is, it is across the integration resistor, and that is charging that integration capacitor. The integration capacitor is right here. Well, sorry, got a little too close. Is right here. And if I put my finger on the integration capacitor, I can cause some changes. 4.8 millivolts. Well, I may have to do some checking, because the circuit seems to work. It seems to integrate quite well at exactly the rate specified in the project, and yet it does not seem to accumulate error. Certainly not at the rate that the author was expecting of 1.6 volts per second, because this unit has been powered up for over 10 minutes now. So let's come back in another 5 or 10 minutes and see if it changes more. It's now been a total of 30 minutes, and the output is 4.8 millivolts. I mean, it's about as stable as you're going to find in, a jelly bean op-amp used in an integrator anyway. So I'm going to have to, at this point, say I do not find the kind of offset that the author expected to find. Now, in fairness, this computation was done with a different op-amp. It was done with an LF411. So, in a previous video, I indicated that I had ordered some 411s from the big cat in Dallas, the Mauser, and those have come in. So I think what I'm going to do is try putting in an LF411 in this circuit, the integrator circuit that's up there, and see what it does, and then report back the results. But I had expected, frankly, to find there would be a lot of error, and the error would integrate over a period of time, but it certainly does not with this particular op-amp. I thought, since I have a number of those 3403s, this is the one that was in there a minute ago. This is one I have yet to try, and this is the one I replaced a little bit ago. I thought I'd try some other 3403s just to see what the difference is. And there is a difference. This one, you may notice, with the input shorted, produces about 17 millivolts. But once again, it does not appear to be integrating. And yet I know the integrator is working. Let's go back over and look at the analog discovery at the scope and the waveform generator. First, what we'll have to do is move. Right now I have the input shorted to ground, and I'll have to connect it back over here to the waveform generator, and then we'll try that again and make sure that this is a working integrator. I'll try to hold this relatively steady. What I'm going to do is go down here to the generator and turn it on, and you see at the top. Let me zoom it in a little. You see that we are integrating exactly the same at 1 volt per millisecond, just as the first 3403 was doing. So it's a working integrator. I have to admit at this point I'm somewhat puzzled. Well, let me check this one for a little while and see if it tends to accumulate any error. But right now it looks like that the something, either my circuit isn't correctly wired up or there's something that I don't understand. Anyway, let's go back and try the grounded input and see if it accumulates any error. And with the input shorted, I'll show you once again where we're doing that. This is the input, which is pin 3. Let me pull out the schematic over here again. Take a look at that in case you want to refresh your recollection. That's pin 3, the non-inverting input. And I'm monitoring on pin 8 with the meter. That's where that test probe is on pin 8, right here. And we're getting quite a bit, about 3 times as much error. Let me move this out of the way a little bit, maybe get a better, well, that didn't help. There we are. 15.8 millivolts, 15.7, but it certainly is not integrating any error. If it was integrating at 1.6 volts per second, well, this would be hit up against the rail already, the supply rail, and it is just sitting there very stably with a shorted input. So I'm a little bit at a loss what to say. Perhaps a viewer can point out some kind of error, but the circuit that I'm using is this circuit here. I've triple checked it, and it sure looks to me like it's exactly the same circuit there. It integrates properly at the proper rate. It swings from the negative rail, or about negative 3.9 volts, up to positive 3.9 volts when it integrates. And yet, for some reason, it doesn't seem to accumulate any real error. Now, you may remember that when we first started looking at this, it was 16 point something, and it's now 15 point something. So, okay, well, let's give it 10 minutes and see where it is. Well, I think I have figured out what's going on, at least in part. You notice now that it's 253.2 and seeming to go up a little bit each time. Well, there it went down, but it's been accumulating. It started at about 250, and it's up to 253 millivolts after about, maybe 30 seconds or so. What I did is, if you saw my previous video, you may remember that I inserted a 10K balancing resistor here when the integrating resistor was 10K, whereas the author just has that pin grounded. Now, I have the 100K back in here for the integrating capacitor, but what I've done, see we're up to 253.3, is I've shorted it out. That is, I shorted out that balancing resistor. That's what this little yellow lead is, going from ground to pin 5, which, if you look again at the circuit here, is the non-inverting input of the integrator. And it does seem to be moving a bit more, but it's still not accumulating a lot of error. It certainly changed the offset. Now what I'm going to do is I'm going to pull that jumper while we're watching it right here. 1, 2, 3, now. Boy, the error goes down to 16 millivolts, from 250 something to 16 millivolts. So having that 10K resistor in the inverting input, or the non-inverting input to ground, seems to tame this integrator a great deal. What I'm going to do is put the original 3403 back in the circuit and see if we're back to that very low value of error. Okay, I've replaced the original 3403. This is the one that I had in there, and this is the one I haven't even tried yet. You notice with the shorted input, we only have 4 millivolts of accumulated error. Pardon that that rotating. That's my ceiling fan modulating the light. At any rate, this is very, very interesting. Well, I'm going to try one last thing. I'm going to put that short back in across that 10K resistor. It's the resistor that's right there, and then see how much error we have. And at that point, I'm just going to have to throw my hands up and say I can't figure out why this doesn't accumulate error, because I know the 3403 is just pretty much a pedestrian op-amp. It doesn't have extremely low offset voltage or any of that like some of the more expensive chopper stabilized and laser trimmed op-amps do. So let me short out that resistor and see what happens. Okay, I've put the short back in with the original 3403, and you see that the error goes to 232 millivolts. Once again, I'll pull the short, and it drops back down to 4.5 millivolts, 4.3, and that's with the input shorted. Well, I have to say, I'm just puzzled. Perhaps a viewer can point out the error of my ways, but at this point, I'm, for the first time, unable to duplicate the lab manual. I'm unable to get that 1.6 volts per second of integration due to error. And I think the reason is that for some reason the amount of error in this particular amp is just seemingly zero. I can't believe that's true, but I don't have any other explanation either. So anyway, I'm going to post this just in the hope that somebody will see something that I'm doing and correct it. But for now, I just have to say that I'm a little bit puzzled.